First, I'd like to thank the organizers, and also congratulate the organizers for holding this stimulating workshop. During the past few days was my sunniest days in my life, even though we are all trapped in this dark room. Well, today I'm going to talk about something I have been playing with during the past couple of years. We have been analyzing Horizon 5 hydrodynamic simulations these days, and I'm very much interested in the relations galaxy in clusters has, the empirical relation, understanding empirical relations in cluster galaxies. So today I'm going to talk about the galaxy morphology and their relation with cluster environment. So before I start, I'd like to review a few observational findings. On the right, I'm showing the diffraction of early type galaxies in galaxy clusters. We are as a function of cluster-centric radius. We are using galaxies in and around 93 AB clusters as a function of their absolute magnitude. So you can see there is some luminosity dependence of this early type galaxy fraction, and also there is a cluster-centric radius dependence of these cluster galaxies. Another way to show this is this two-dimensional environment plot. Here I'm using two environmental parameters for galaxies in galaxy cluster. One is the distance from the center of cluster, the cluster-centric distance. The other one is the environment provided by the nearest neighbor of cluster galaxies. And that has two parameters. One is the morphological type of nearest neighbor. The other one is the distance to the nearest neighbor galaxy. So here, these blue dots are early type galaxies, and red dots the late type galaxies. The blue ones are red type galaxies. And on the right, I'm showing the galaxies having early type neighbor. And on the right, they are the galaxies having late type neighbor. And the contours show the elliptical galaxy fraction. And the fact that they are horizontal means it's independent of cluster-centric radius. It's outside the virial radius. And it's monotonic function of the distance to the nearest neighbor. But it's different, completely different, depending on whether or not this neighbor has early type morphology or late type morphology. So if you have late type, early type neighbor, your probability of being early type galaxy monotonically increases, whereas it goes opposite direction if you have late type neighbor. Once you enter cluster virial radius, the situation changes completely, and contours are all vertical, which means the influence of neighbor is quite weak, and morphology is a strong function of cluster-centric radius. Another conclusion one can make is this. So from 10 times the virial radius to 1 times virial radius, there is a lot of local density increase, but you see it's really independent of density, which means there is no morphology density relation. You appear to observe it because local density it has a statistical correlation with the nearest neighbor distance. So as you go to high density, your neighbor is statistically closer, but it's actually neighbor which is changing your property. Okay, so that's the morphology, and here I'm showing star formation rate. I'm going to show U minus R color and HR per equivalent width. Here the contours looks different. here the contours are more or less horizontal, even inside the cluster virial radius, which means it is really the nearest neighbor which is affecting the star formation activity of galaxies. So here the cluster galaxies having the early type nearest neighbor, and here is the cluster late type galaxy having late type nearest neighbor. And again, when the distance to the nearest neighbor is shorter than the virial radius of neighbor galaxy, then you are strongly affected by the neighbor. And the direction is opposite depending on the morphological type of your neighbor. You see the similar dependence for the equivalent width of H alpha 9. Okay, so that's short review of observational findings. One can ask, when did these relations start to appear and why they are appearing? So to answer these questions, I'm not answering all of this, I'm studying it right now. We use Horizon 5 simulation. So let me briefly introduce this simulation. This simulation used hybrid MPI plus OpenMP Ramses code, and it adopted the flat lambda CDM with omega matter 0.3. It has simulation box size of gigaparsec, and it has zoomed in region at the center of box, which has this size. It's a gigaparsec by about 100 megaparsec by 100 megaparsec. And in that zoomed in region, it has the resolution of about 1 proper kiloparsec. And we use stellar mass density to measure the galaxy morphology. And the parameter we use to classify galaxy morphology are two. One is asymmetry parameter. The other one is the Sungwook index. And we classify galaxies into three classes. One is irregular, and disk, and spheroid. We first use asymmetry parameter. If this is smaller than 0.4, they are the symmetric galaxy. If it's greater than 0.4, they are irregular galaxies. And for symmetric galaxies, we measure the radial profile and try to fit Sungwook profile. If the fit fails, then it becomes irregular too. But for the galaxies where the Sungwook index can be calculated, measured, then they are regular galaxies. If the Sungwook index is less than 1.5, they are disk type. And if it's greater than 1.5, it's spheroid. Here are some examples. So disk is like this, and spheroid is more concentrated centrally, and irregulars are often interacting. Okay, so the result. So we looked at the galaxy morphology at redshift before z equal 4, and found that most of galaxies are disk type. So 2/3 of galaxies are disk type, 2/3 at redshift 8, 7, 6, 5, 4. They are all about this. And 1/6, about 15% of galaxies are spheroid, and another 15% is irregular. And they are more or less independent of mass. And we try to understand why galaxies are having mostly disk type, and found that their angular momentum, the angular momentum of the total mass, including dark matter, and angular momentum of stellar component, they have very tight correlation with the initial angular momentum generated by the old material in the initial condition around the galaxy. So we use the moment of inertia tensor and shear tensor to calculate the initial angular momentum, and looked at how their angle correlates with this actual galaxy angular momentum vector at later epoch. And with the total mass, there's a very tight correlation, and there's also some good correlation with the stellar components too. So we think the large-scale tidal field, or the velocity field in the initial condition, is actually responsible for the dominance of disk galaxies at high redshift. And also, whenever these disk galaxies are destroyed to become irregular or spheroidal, they reacquire disk morphology later because this environmental, the gas is falling in to recover this disk morphology. Okay. What about the spheroidal and irregular type? There are 15% of spheroidal and another 15% irregulars. To understand this, I'm showing this. So here are 4 randomly chosen galaxies, and I'm showing how their searching index evolves as a function of mass. So they are moving this way. So as they acquire mass, most of the time they lie below 1.5. So I call them their disk galaxy. But occasionally they have a searching index larger than 1.5, and then they come back. So they reacquire disk morphology. And then they fluctuate and sometimes go down as well. So I conclude this irregular and spheroidal morphology is incidental and transient one in this high redshift era. Okay, so what about the galaxies in clusters? Because that was for general galaxies. So to study, to understand this relation, empirical relation we found for cluster galaxies, we selected 162 the galaxy clusters with mass greater than 5 times 10 to the 13 solar mass at G equal 0.26. We chose this because this is the end of the simulation. We ran out of simulation time, so we couldn't go quite G equal 0. Then there are about 4,000 member galaxies belonging to these clusters, and we trace all of these member galaxies along the merger tree. Okay, so here we try to understand the relation between mass and morphology and cluster central radius. So let's look at this panel. So in this panel, I'm showing the searching indices of cluster member galaxies identified at the final epoch of simulation. And then I trace back to their progenitor and measure their searching index as well. And this is the cluster central radius as measured in units of virial radius at the final epoch. And you see, so the color represents the stellar mass of individual galaxies. So these galaxies are basically the central galaxies. And you see at redshift 2.6, for example, the searching index at the center and the searching index of the galaxies that will become member later, they all have almost the same searching index. So the searching index radial profile is flat at this redshift. And you see the searching index at the center is rising. So there is kind of special epoch of the universe where this morphology cluster central radius relations start to appear. And that is about redshift 2. And by redshift 1.5, which I missed here, but after 1.5, this relation is quite well established. At very late epoch, you see the searching index of the galaxies at the center start to drop a little bit, and that's mostly because of these disk galaxies coming in near the center. The massive galaxies continue to be compact, but there are some new galaxies reaching the center. So that's why this is decreasing. Okay, so this is the same kind of plot. Here, so this line is showing the galaxies sitting at 10%, within 10% of the cluster radius, and the left one was the galaxies at the outskirts of the cluster. So the galaxies at the outskirts of the cluster evolve this way, and the galaxies at the center, basically the central galaxies, evolve this way. And at high redshift, even though there is a huge mass difference, their source index is not much different. But depending on whether they are central galaxies or future satellite galaxies, the evolution tracks are completely different. So, for example, at this mass scale, even though they have same stellar mass, their source indexes are quite different. So we conclude that morphology depends not directly on mass, but on the galaxy location in the cosmic web, and also how galaxy acquires this mass. Because by this time, these central galaxies are acquiring their mass mostly through merger, but the galaxies at this point is collecting their mass mostly through accretion. Okay, because I'm running out of time, I should hurry. Okay. So now let's look at the bottom panel, which is showing star formation rate of individual galaxies. So again, I'm tracing back along the merger tree, and at high redshift to low redshift, this specific star formation rate is monotonically decreasing everywhere. But you start to see there is some the gradient appearing after z equal 1. Okay, and we conclude that this star formation rate and cluster-centric radius relations start to appear here, okay, at g equal 1, except for the central galaxy itself, which is getting a lot of the satellite galaxies being merged. Okay, and the reason that these galaxies are becoming inactive, I think, is because they are getting any mass. Once they cross the virial radius, their mass growth stops. So they only burn their own material, the fuel, and the only way to evolve is to getting fainter and fainter. I mean, the star formation rate is decreasing. So basically the mass is fixed, and the star formation rate just monotonically decreases. Okay, so let's look at this one. This is I'm showing the morphology fraction as a function of cluster-centric radius. This is the disk galaxy and spherical galaxies and irregular galaxies. And these disk galaxies can be divided into passive one and the active ones. And you see most of the disk galaxies are passive by this time. But if you go to redshift 1, most galaxies are active galaxies. So there is the reversal in this fraction between passive and reversal, active galaxies. Okay, so this compares with observation. You see, this is Dubocler's plot for clusters. So as you go to the center, as you approach the center, the fraction of ellipticals are almost constant, but only at the center, it suddenly rises. Okay? And that's exactly what you see here. We have a lot of irregular galaxy fraction right at the center, but I believe they will probably become spheroidal by z equals 0. So they probably double this value. So there's almost a flat and then suddenly rises. So that's exactly what you see. And majority of cluster galaxies are actually disk galaxies, but they are lenticular. So they are passive disk galaxies, which are here. So we are more or less recovering these observational findings. Okay, to summarize, we use horizon 5 simulations to study the empirical relations we found for cluster galaxies. For high redshift, for luminosity mass or morphology cluster central radius relation, these start to appear around 2.5 and then become established at 1.5. And we think the strong interaction and high merger rate is responsible for this relation. And this is indicated by large irregular fraction at the center. For star formation rate, it starts to emerge at z equal about 1. And I think it's mostly because of this disk galaxies becomes passive after z equal 1. There are a lot more things to be understood, which is ongoing right now. Thank you.
Hi, thank you. It's nice to see morphologies in a talk. Although it would be great to see what happens to the sizes too. I have two questions. One is related to the first part and one to the second. So first, real quickly, when you talk about neighbors outside of the clusters, can I understand that as a proxy for filaments? If it's closer to another neighbor, it might be more likely to be in a filament?
The neighbor galaxy?
Yeah, you used
neighbor to the
you
cluster?
used neighbors. Yeah.
So when we say a certain galaxy is a neighbor, you just look for the nearest neighbor galaxy, which has luminosity not fainter than half the luminosity of your own galaxy. So we are not paying attention to filaments or any other things.
No, I understand, but
you just look for the nearest neighbor galaxy.
Yeah. I'm just trying to connect it in my head to a cosmic filament, if they might be.
So actually, I was invited to give a talk at the European Astronomical Society meeting in this July. So that was about filaments. So I should hurry to study this filamentary effect after this.
And then I think you said when the Cersei fit fails, you classify it as irregular. Why is that? I mean, especially in crowded fields, it's difficult to correctly get Cersei indices. So what tests have you done to be confident in your measurements?
The classification between irregular galaxies and non-irregular galaxies is actually not very so concrete thing, because it really depends on how far you use in the radio profile. Because as you go farther away, the radio profile can start to fluctuate. Then your Sungwook fit fails, because Sungwook profile assumes it's monotonically decreasing. And so if some galaxy has some the merger feature inside, so that the density profile can oscillate, then you fail. And
so what did you use for your morphology measurements?
The stellar mass density, the radial stellar mass density profile.
And you fit that
such a profile
yourself,
right?
Okay.
Thanks. I'm curious about the second bullet points where you touch upon quickly about the morphology of this disk type galaxies, where you said that it's basically imprinted by the initial angular momentum. And the angular momentum comes from the initial conditions, basically. So, and if I remember correctly, you mentioned that even in the case where two spirals merge and later on they turn into spheroidal, and then later on they could turn into spirals again because of that condition. Is that correct?
Right, right.
Yeah, so that's quite a kind of a new image to me. I wonder if there's any hints of in observation we can follow up and see that.
Right. So physically speaking, if you have two disc galaxies and they merge, then their angular momentum vector can flip, and also their morphology can become irregular, and then after some time they relax and becomes more spheroidal. But by that time, there is large-scale mass info still remembering this initial condition. So they are adding this angular momentum so that this galaxy evolved back to disk galaxies.
Yeah, I understand the logic as well, but I wonder if observationally there's any evidence for that.
Observationally, no. From simulation.
Yeah, I know.
Do you count as one of the observation? In the simulation, we are observing this. This is what we observe. See, it became spheroidal and then go back to disk.
Yeah.
Okay. So this is our observation.
Yeah. Right.
So when you're studying this, when computing all these cluster-centric quantities at different redshifts, so when we study like the growth of clusters, even in your video, it's clear that the center of mass of the protocluster moves through as time evolves.
Right.
So how do you define the center of the cluster in this calculations? Is it the barycentric center of the Lagrangian mass, or did you fix the Eulerian position?
Yeah, exactly. So we just fixed the center as the center of the density peak at the final epoch. So we are not actually following these things. So the cluster-centric, the central galaxy of the galaxy they are not exactly at R equals 0, but they are moving around.
Thank you.
If we consider that you measure the surface index for the cosmic morning galaxies, of course, in observation, there is some massive disk galaxies in the high redshift is found recently, but in simulation, as I know, there is just some time is required for galaxies to develop a stable disk in the galaxy simulation. Then is it reasonable to use the surface index for the unstable, the galaxies with unstable morphology, kinematic structure, still be reasonable to using some intrinsic, the proxy for the intrinsic kinematic structure of the galaxy?
Well, okay, so we treat galaxy morphology as quantity which can evolve. Okay? It's not some intrinsically fixed property of galaxies. That's why the search index fluctuates a lot. Okay? And at certain given time, you see this galaxy has very nice the search profile, having exponential disk. But the next step is suddenly become wildly different because of the strong interaction with the neighbor galaxies. So they are not stable. They evolve quite quickly.
So the basic assumption for the analysis is that the intrinsic kinematic structure, for example, like V of sigma is proportional to the surface index at some reasonable range of the redshift, at all redshift.
The morphology and V of sigma and also the color property and so on, they are we know they have very tight correlation at low redshift.
Yeah, at low redshift, yes.
That's not true at high redshift. So it's very wrong to talk about galaxy morphology based on V of sigma. at high redshift because they developed property at much later epoch. So you better, when you talk about morphology, you really have to use morphology, the shape of the galaxy. The kinematics you study separately.
Is there another question?
When you were showing the plot with the alignment between the TTT prediction and the spin, did you also try looking at the correlation between the amplitude that is predicted and the amplitude that you measure for the spin? So not only the direction.
Amplitude of what?
The amplitude of the spin. Does it correlate well with the amplitude of the TTT prediction?
We didn't look at the amplitude. Yeah, only the angle between two spin vectors.
Okay, so let's thank Changbom.
Thank you very much.